Okay, we'll get started. Welcome to today's Grand Rounds. We're privileged and honored to have Dr. Jill Tardif here from University of Arizona giving us a talk about hypertrophic cardiomyopathy. So before I introduce her, I will just give a personal touch to the story. I've known her since I finished my fellowship, and she's been very instrumental in my career development, and the grant that I'm funded from NIH, a significant portion of the experiments are based on a mouse model that Dr. Tardif has created, and she's going to talk about some of that data here. So now, to introduce her, it's going to take some time, and I think there's a class after this, so I'll be very short. She's a professor of medicine and professor in cellular and molecular biology at University of Arizona. She's vice chair of research. She has been there for a few years, but she started in the West Coast, went to the East Coast, and then kind of came back. She did her undergraduate at UC Berkeley, did the MD PhD program at Albert Einstein, and did her clinical training in New York as well in internal medicine and cardiology. She was mentored by, during her fellowship, by a very well-known basic scientist, Dr. Leslie Linewand, and got her KO8 in 2002, and then RO1s continuously since that time. She rose through the ranks there, becoming associate professor in 2011, and then moving to University of Arizona in 2012, becoming a professor of medicine. She is involved with the American Heart Association. She's reviewers in some of my favorite journals, like Biophysical journal, and some of your favorite journals, including Circulation and JACC, and she's on the editorial board for JMCC and many, many publications. A very impressive CV, and we're very delighted to have her give the ground rounds this morning.
Disclosures of which I have none. I always joke about my only disclosure is that I'm a Mets fan, which is probably something I should admit to. So today I'm just going to go through, we're going to talk about hypertrophic cardiomyopathy. And what about that hypertrophic cardiomyopathy that all of us learned in medical school, which I'm discovering from interacting with my medical students in Arizona, is really a very different deal. And so I thought I would spend a little bit of time reorienting everyone with regards to sort of the modern view of the disease. Tell you how we're trying, or we have been trying for many years at this point, to understand how to incorporate the genetics of the disease. This is a genetic disease until proven otherwise at this point in time. How to incorporate that and develop molecular mechanisms that actually we can use to treat patients in a more direct manner. And that's a real continuing issue in the field. I will admit that there's a little bit of frustration for those of us who take care of these patients and who also do the research, in that we've known the genetic background of this disease now for 27 years, and we still really can't use genotype to prognosticate. And for those of us like myself who remember vividly when the first linkage analysis proved that myosin heavy chain was linked to HCM, trust me, in the field, there was quite the happiness. Everyone said, oh, I knew it was, that usual thing. But there was a lot of happiness because we figured, okay, now we're going to nail it down. We're going to understand this disease. It's all going to be different. Well, 27 years later, which sort of makes that, we're still not using genotype. So there's a lot of really great work to be done. And so this is hopefully a hopeful talk. I'm going to talk just a little bit about some of my science. I'll sort of bash through that a little bit, but just to give you a flavor of the way that we're trying to think about it in a more robust way and where we really want to go in the future. And there's a very specific reason that it's imperative for us to finally get our act together, as I usually say, about using genetics to treat patients. And I'll get to that in the end, then of course next steps, which are always fun. So here's the HCM we all learned about, and again, I'm not casting aspersions here. This is the one I learned about too. Right? Unexplained left ventricular hypertrophy. If you take 1,000 people, and this has been done repeatedly both in Europe and here, and you perform an echocardiogram, and you look at the heart, 2 of those 1,000 are going to have unexplained left ventricular hypertrophy. In other words, they're going to have a hypertrophied LV. They're goes my voice. Hypertrophied LV with no obvious cause. No valvular disease, no essential hypertension, and we're sort of left with what is the cause. These are delightful, this is from the 2011 guidelines. This is always delightful, wonderful for the fellows, of course, as they memorize these things. The only point I really want to make here, and you can barely see it, but trust me, here's the obstructive lines. You take a patient, are they obstructive or are they not? I will point out from my practice, I also am the director of the Hypertrophic Cardiomyopathy Clinic at Arizona. It's really the main genetic cardiomyopathy clinic actually in the Southwest at this point. The decision tree is obstructive or not, and we look for these obstructive patients because we can actually perform myectomy or, in rare cases, alcohol septal ablation to relieve the outflow tract obstruction. But what are our drug options? Well, these should sound familiar. Beta blockers, calcium channel, or dihydropyridine calcium channel blockers, so verapamil or diltiazem, and disopyramide every once in a while. Okay, so this is probably what we were using back in the 70s. This is not exciting stuff, quite frankly. And over here, once the patients who transition to systolic failure, you treat them like a failure patient, and you set them up for transplant. About 5% of all the sarcomeric positive patients. This is not very satisfying, or I hope no one's satisfied by using the exact same therapy we've used for 40 years. I know I am not. What happened in 2011? So, and again, this treatment is all symptom-based and palliative. This is really important. Okay? We tend not to treat patients who are asymptomatic. We are transitioning to that a little bit, and I'm going to touch on that and just keep that in the back of your mind. Here's the new definition. So here's the unexplained LV hypertrophy associated with blah, blah, non-dilated ventricular chambers. And now this caveat. Patients who are genotype positive, meaning they have a known pathogenic allele, and I won't really talk about the genetics today because it's quite a quagmire right this moment, may be phenotypically negative without overt hypertrophy. Okay, so what does that mean? This is actually where the problem comes. So who has the disease? Is it because you have a sarcomeric gene mutation and your heart looks normal? Or do you have to have hypertrophy? Because if you wait until you have hypertrophy, more recent data would suggest you're already behind the 8 ball. You've already moved past the point at which you're going to have a real effect in terms of possibly regressing the disease. So what are we supposed to do? And this is very, very important, and I cannot overemphasize how this has changed how we think about the disease and basically made everyone's clinics much more complicated. As I said, it's a genetic disorder until proven otherwise. The classic form of the disease is caused by mutations in proteins that are components of the cardiac sarcomere. So if you reach back into your recesses, back when you did basic biology, the sarcomere is this, I'm a structuralist sort of at heart, so to speak, and so, many of us ended up doing this because we're so fascinated by this system. But basically, just remember, this is the sarcomere with the thick and the thin filaments. They move past each other to generate force on the molecular level. That is transmitted to the whole heart via the fact that each one of these cells, that's all they do. And you've all seen pictures. You all probably remember from biology. If you pull out a myocyte and you stimulate it in a dish, it's going to beat. So these are the structural proteins that drive that beating. This down below is a model of the thin filament, which is responsible for calcium regulation. Remember, calcium activates through excitation connection coupling, calcium-induced calcium release, all of these things, where basically if you hit the cell with an action potential, you stimulate calcium to flow through that channel and activate calcium release from within the sarcoplasmic reticulum and generate action to activation. Okay? That's exactly how the heart beats at the molecular level. This model, and I'm going to see it a lot. I'm going to just point it out quickly what it is. This is talking about 1,600 mutations in 9 proteins. So imagine the degrees of freedom in this question. And varying penetrance and expressivity, variation. The key point here is that this is not a monolith. This disease is protein in its phenotypic expression. I'm going to explain why in a moment. This model, coming back to this, is actually a computational model. It's an all-atom model. 5 million atoms mapped in space and followed. And it's sort of, excuse the term, a delightful toy box. My collaborator who built this would not enjoy that description, but he doesn't have to know. So what has been the effect on clinical practice of this new, as of 1990 definition, or I'm sorry, 2011, this definition of the disease that's genetic until proven otherwise? Okay. Well, it's really simple. So my patients up until about then, most of them, it was really much more, probably around 2000, is unexplained left ventricular hypertrophy. And what does that mean? The patients that I see have symptoms or someone stumbled on their hypertrophy without an obvious cause as part of a workup. All of them all of them had significant cardiac remodeling by the time I would actually see them in clinic. So we're already sort of past the go point, right? These patients have already had pathogenic remodeling, and if they're adults, it could have gone on for decades. That puts you at a different stage of the disease, and this is where the definition of HCM comes from. I think you can imagine that at this point, how genetics changes things is that the people I see now, a number of them, say about 20% or so now, the younger ones in particular, is that someone in their family has been diagnosed with a gene mutation. So they immediately get referred to me, either for targeted testing to see if they have the mutation as well, or someone in their family had sudden cardiac death, or else they've already been genotyped, and they show up with a phenotypically normal heart. So what do they have? We would argue, most of us, that they have the predisposition to develop HCM. And for those of you, for example, who take care of patients with other cardiac diseases, I would think that the heart failure being the classic one, you can imagine in a way what an amazing advantage that could be, right? If we knew which diabetic was actually going to go on and develop heart failure, that would really change our management, wouldn't it? That would change everything. So here we have that in HCM. I know who has the predisposition. Does that mean they will develop the disease? Not always. That's my complexity I have to deal with. But so I think you can see how this has sort of been excuse the term, torment for those of us, is that we really do have an idea who's going to develop the disease. So now the onus is on us to do better research and to better understand how the molecular basis of the disease actually expresses itself. So several years ago, one of the things that happened since we were able to genotype patients, and genotyping has become much more affordable, and so we're genotyping a lot of people. So again, my practice is changing, so that's interesting. But we also develop longitudinal studies, and I was part of one of them, and there have been several others, and for those of you who pay attention to this literature, there's the SHARE registry, which is going to revolutionize this field, I'm pretty sure. In that case, the SHARE registry, which grew out of the Thin Filament Consortium that I started a number of years ago, has, at this point, over 6,000 patients with a form of HCM, and 3,500 of them have been genotyped. It's an amazing resource. That is truly a toy box for those of us, because we can now follow, and they've all been followed. So we can actually follow the progression of the disease, track it better, say, to certain mutations or certain, as I will show you in a moment, certain biophysical changes that have led to the disease, and start to map out the disease in a much more coherent fashion. So you see where I'm going with this? That maybe we can think of a way to classify the disease into, as we call them, bins, different people with certain functional effects at the molecular level, defining certain arms of the disease. You can see where we're going with this, because targeted therapies in that point may allow us to really have a much more appropriate and useful approach to these patients than simply giving them all calcium channel blockers and beta blockers and wondering why they don't work. So with all of those longitudinal studies a couple of years ago, all of a sudden our literature changed. Now all of a sudden, instead of unexplained left ventricular hypertrophy, we have altered myocardial structural alteration, preclinical hypertrophic cardiomyopathy. These are these patients, genotype positive, phenotype negative, G plus P minus. Sarcomere gene mutations without clinically overt. I mean, what is this? This is a whole different ballgame. These are these patients I'm talking about. And as I say, even in DCM, early manifestation of sarcomere mutations, and this is actually mine, never too early to look. This is a sea change. Really have the opportunity, if we can figure out how and if we can figure out what to target therapeutically, to change the natural history of this disorder. This is not a minor deal. Again, it's important to remember that most patients with HCM, most patients, this is not an exaggeration, live normal lives. And that's something I often forget to remind people of. We have this picture from the older literature, which was pretty much covered, with a referral bias from the Mayo, right? Because that's where all the difficult cases were sent years ago. And they published all the papers. So this view of HCM is this deadly, everyone dies sort of thing. And these are the sorts of views of the disease that my patients come to see me with. The first question to them always is, tell me you didn't Google this disease, right? Because the first 6 pages are dead people, dead young people. It's truly terrifying. I mean, I've had, patients truly terrified when they've been referred to me because it's their death sentence. Go see the sudden cardiac death doc. And, it's really amazing. And, especially where I am down in Arizona, where, we have a lot of outlying areas, and people just don't know. And the docs don't know. And the cardiologists who don't see enough of these patients don't know. So it's a very difficult thing. So especially for you fellows up there, to be sensitive to what the real view of the disease is and what the perception is. We can take care of these patients. The most important thing is to find those that are at higher risk of sudden cardiac death, find them, and that's a challenge, and also to figure out better approaches to keep the disease from progressing, because still 5% of sarcomere-positive patients need transplant, either for restrictive or for systolic failure. All of you know that putting off I'd rather transplant a 62-year-old than a 42-year-old, right? So changing the natural history of the disease by targeting it earlier will have an enormous effect on a lot of people's management, and I think have a very important effect on the disease. So here's the problem. So I've been showing this slide in some form literally for decades myself. This was back in the 90s when I decided to not be an endocrinologist and instead be a cardiologist, knowing the head of endocrine at Columbia to no end. I don't think he spoke to me for about 5 years. So in any case, how do we take these biophysical mechanisms, the effects of these genotypes, and turn it into a progressive disease? Because that's the problem. This is a disease of timescales. What happens between this mutation and decades? Patients show up in their late 20s, their 30s. Many of my patients in the last few years, for some reason, have been showing up. There's a lot of water under that bridge in terms of cardiac remodeling, right? That's a long time. And I think that should feed into what I said in terms of most patients do okay. Now, some are horribly symptomatic by that point, but many are not. An important thing to know, by the way, is that the risk of sudden cardiac death, most people actually think it gets worse as they get older. That's actually not true. As patients get older, their risk of sudden cardiac death goes down quite precipitously. So when I see a patient at 60 who's been diagnosed, their chances of having, because mainly the issue being that if you're going to have SCD, you're going to do it early. You're going to declare yourself. Something to know in general. So what do you do with this? What do I do with this? What do any of us do with this? So more recently, we've been trying to take everything that we're learning from these progressive studies and put it into a paradigm that I think is very useful. And, I'll show this throughout the talk with all sorts of added things to it. But this is the essential issue, that's the essential way I think hopefully you'll take home if you're going to be thinking about the disease from the molecular all the way to the patient level. That if you take these myofilament mutations, these mutations in this, as I say, we're all in love with the sarcomere, which is sad, but this structural concomitant of contraction, the most fundamental unit of contraction, and you try to figure out how you get to here, probably the best way to think about it is that these biophysical manifestations, these mutations that change the function of the cardiac sarcomere, act as a trigger. As we all know, and many of us, I think who went into cardiology, probably went into cardiology because of the flexibility of the organ. It's really quite an amazing machine, right? Can you imagine many other machines that can beat for 80-odd years and never stop for any, presumably long period of time, and beat with perfect fidelity in many cases, no matter what we do to it? That's all about this compensatory issue, and this is all about the cell responding to perturbations, extrinsic or intrinsic stresses. Really pretty remarkable when you think about it. So the myocyte has developed an amazing, evolved quite frankly, an amazing compensatory mechanism to take the cellular response to these biophysical triggers, these problems with how the actual function of the sarcomere, and respond to them to maintain cardiac output. That's really all the heart cares about, right, at the end of the day. And it can do it on the molecular level. And so what we think happens is that there are these triggers, these perturbations. The heart responds during this period of time in green here. This is that genotype positive, phenotype negative time. And this is what I like to call the churn. This happens with these different pathways being set off as they try to support the heart against this intrinsic, permanent stress. And how well the cell responds determines the length of time that this goes on. This is, as I say, prior to the development of pathogenic remodeling or pathologic remodeling, where the heart's starting to go off the rails. This is when the compensatory phase starts to fail. This is when the heart really begins to remodel and ends up here, where you have symptoms, sort of in here. The key point being, and sort of the take-home here, is that if we're going to intervene, we want to intervene either here or right in here. We want to take this compensatory phase, because I'm not going to argue about gene therapy right this moment. I'm a geneticist by training. This is not where I think we're going in this field, quite frankly. So we need to take this period of time and lengthen it. We need to figure out what those compensatory pathways are, how can we intervene to make that compensatory time longer, and stave off this stage. That's the easiest way to think about the molecular pathogenesis. So in my lab, this is what we do, and I won't go through this slide completely. But I started my life, of course, from a cardiovascular. I was joking about having to retrain from endocrine after my intern year at Columbia Presbyterian. And this is for the trainees out there. Trust me, I didn't know anything about either the myofilament, except what I learned in medical school in the 80s, or mechanics, or computational biophysics, any of it. I had to completely retrain when I changed my interest as an intern. The only reason I point that out is that anything is possible. If I can turn myself from a metabolism, liver metabolism, gene transcription factor person into a credible biophysicist, you can do anything, right? So that's what I had to do. So I built animal models because I will point out, from my perspective, you can't study a progressive disease fully without an animal model. What does it mean to study a progressive disease in patients just in a dish? It's not that I don't think in vitro studies are important. Obviously, I do lots of them. But in isolation, there is no one true path to getting the answer to this disease. And trust me, I've learned that one the hard way, as have many of my colleagues. Because many people live sort of in one bin. So I've literally spent the last 10 years within my laboratory and with a collaboration with Steve Schwartz in chemistry at Arizona, building a coherent combinational approach where I can match computation that Steve does to very specific biophysical measurements and couple the two, because that's going to give me power to predict eventually. That's the goal. The hardest jump is over here to the murine models, but I'll talk about it. I also just want to remind everybody, and then throw my clinical hat back on, you know, at the end of the day, and I think we all know this, this is where translational medicine, translational science, precision medicine, whatever you want to call it, is at its strongest, because as clinicians, we know what the real questions are, right? How many times have you gone to a pure basic science talk and sort of scratched your head like, boy, this person actually really probably doesn't understand this disease very well, right? This just happens all the time. And I think as clinicians, this is a really important role that we play to identify those questions via studying the share registry, studying your own patients, and identify different questions that we can ask that actually are clinically relevant. One of my favorites that I really want to talk about today is actually time of onset. When that, in other words, that picture I showed you with the compensatory phase, when do patients become symptomatic? That's really important, right? Because obviously we want to intervene before that. But that's different, we're finding, for many of the different mutations in different proteins. Can we harness these sorts of studies to ask really great questions? That's sort of what we've been trying to do, quite frankly, over many years. This is just to give you an idea of the sorts. The other point I want to make, oops, not that. The other point I want to make is, so here are your triggers, for example, and here are all the things that can happen at the biophysical level. You can change calcium binding, dynamics and structure, you can change cross-bridge. These are just sort of details here. Leading to all of these compensatory secondary responses down below, abnormal calcium handling, downstream signaling, some transcriptional activation, all of these things. This is just a small snapshot. The point I want to make, and probably one of the most important take-homes, not every mutation in the sarcomere hits all of these things. This is truly a mix and match. And we've shown this, other people have shown this. The specificity of these given mutations for these pathways is actually profoundly exquisite. And I've chosen two little vignettes today, as I say, that I'll go through a little quickly, but just to give you a flavor, that show that, I think, beyond what we thought we were going to find when we started doing this work. And why is that important? Because I think it starts to give you an idea of why the disease is so variable. And that's a little bit of the holy grail, right? Because I told you, you see all of these phenotypes. What do I do with them? How do I link genotype to phenotype in a disease that seems to have an endless number of phenotypes? How does that work? And there's a period of time back around middle aughts where there are all these papers over and over and over again, basically from the geneticists, my colleagues, basically saying, forget it. Good luck with that. We have, X number of, 1,600 mutations. It seems like we have 1,600 phenotypes. Good luck in figuring that out. And a lot of us got annoyed by this. This is Mike Ackerman. But we're going to prove that guy wrong. So in any case, let's go to a clinical question. How would mutations that affect the same functional domain in the thin filament, we're talking about thin filament today, Generate divergent patterns of ventricular remodeling. This is actually kind of a cool question. So this is part of the structure of the thin filament. I'll get to this in a moment. These are two of my mouse models, actually. You can see here with a dilated cardiomyopathy model, that's pretty good. Big chamber, thin walls, pretty nice. Here's a HCM model, thick chamber, small chamber, thick walls, big atrium. These mutations, one in TNT in yellow, one in tropomyosin in green here, these two mutations affect the same structure. Yet, could these be more different? These are so obvious that we can see them in mice. One of these is Farhid's mouse, it's down here. One of these, this is just not subtle. We can't be blinded, none of that. So how does that work? Well, I'm not going to go through this very much. Here's just the thin filament to remind you, for those, or show you. This is that atomistic model, 5 million atoms. I always have to point that out, because developing this model, so you're just seeing this sort of 2D static representation, and I'll talk about what this model really is in a moment. This took 10 years to come up with this. This was 2 individual students' PhD theses. And it's an incredible tool. I'm using this just to show you where everything is. So here, down here is the overlap again that I just showed you. Here are 2 mutations, one R92L and R92W. And if you're looking at this, you're like, whoa, wait a minute, that's the same residue and different amino acids. I'm going to show you how not only are the patients different, and this was my first R01 15 years ago, not only are the patients different, but so are the mice. And that, if you're a physical chemist or interested in sort of great questions, nothing gets better than that. The important point I want to make is that here's the overlap, and here's where calcium binds. And I'm not going to go into the allostery in the system very much in this talk, but just to let you know that mutations get propagated. They get propagated through, when you take a helix, a long alpha helix, go back to biochemistry, and you change some property about that helix, it gets transmitted through that helix. If you compact it at one point, it has to open somewhere else, right? Potential energy. That has to happen. This is the way the system is built. It's hardwired for this, right? Because I told you calcium activates it. It activates it. It hits. It basically isomerizes at this part, the core, and changes the position of tropomyosin, which moves across actin and allows myosin to come in and generate a cross bridge. That's how activation works. It's really literally that simple. So if it's hardwired to work that way, it's not that crazy to say that a mutation here can affect this part of the molecule. It certainly isn't crazy. I'll quickly show you, and many other people have now pointed this out. I just want you to think about, from the biophysical standpoint for a moment, how that changes our thinking. Because if we did a biophysical assay, any of them, we put a mutation in here and say we did an assay, and we got an effect. We're looking for sliding speed, we're looking for calcium sensitivity, any of those sorts of things. The assumption, obviously, would be that, okay, that function is driven by this location, right? That's what is governing what you're seeing. That's actually not true in many cases. This sort of amazing structure. I'm going to show you that. Just to tell about computation, because I think it's neat, and I think it's useful to know, because you're going to hear about things. So for those of you who know about rational drug design, for example, a lot of it is based on molecular dynamic simulations. And all this is going back array to physics, Newton's second law, F equals ma. All that these simulations are is you take one of these structures, at time 0, you plot the position of each alpha carbon, each atom, more or less. And then you run the simulation over time in silico in a computer. Big computing power for these things, enormous computing power. Some of the runs on these models I've shown you can take 3 weeks on a really large computer, not someone's PC, in what could only be a mini supercomputer. We actually do run some of these things at some of the big computing centers. And then since you know the force on each atom, you can then measure, right, force equals ma, the acceleration of each atom, and over time, after you integrate these equations of motion, you know where it goes. So it gives you dynamics. It shows you how each atom is moving in space, and it can basically tell you movement, dynamics, and structure as it equilibrates into a new structure. Very powerful if you know what you're doing, and this is one of the nice things about dealing with my collaborator, since he's really not a biologist like at all. So it's very useful. So there's no crosstalk on that one. This is not plug and trug, okay? I just want to make the point, you don't buy a program and stick this in. This is actually non-trivial. And we were really constrained by a lack of structure. So let me sort of dash in. So these are where the mutations were. I told you this already. One is HCM, the RL, and D30N, DCM. This is what that overlap looks like. A very amazing structure. You take two tropomyosins, which each one is an alpha helical coiled coil, if you guys remember from biochemistry. That's what you learned. You learned about tropomyosin as the canonical alpha helical coiled structure. One mutation is here in troponin T, which stabilizes this overlap. This is a swivel, profoundly flexible. I'm not going to go through all of this. A lot goes on at this overlap. Very busy part of the molecule. It has long been described in my field as the Bermuda Triangle because it's moving so much it could never be crystallized. Okay? It's very hard to study because no one was really, if you can't get a crystal, you really can't even get a starting point for where everything's supposed to be. And what followed was years of work trying to figure this out. So let's start from the beginning. How am I going to study how those two mutations cause two different phenotypes? So let's do some echoes. So it made two independent mouse models. Here's the RL right there. It's about 50-50 transgene here and endogenous, so that's nice. D230N's about this. We took mass spec to do this, which was really not very much fun. About 60%. So this is the mouse that Farhid works with, and this is R92L. TNT, hypertrophic, DCM in tropomyosin. Here are what the echoes for these work. That's a normal 2-month-old mouse. Pretty good. Nice squeeze, nice relaxation. For those of you who have really good eyes, pay attention. You can already see this is real thick, so that's the hypertrophic one. Nice small chamber. Take a look, see if you can see the relaxation. How normal that looks. You can even see it almost fair, right? You can see it's really tons of diastolic dysfunction in these animals. Okay, so that's pretty. Every single patient, more or less, who has HCM, by the way, has diastolic dysfunction, as you probably know. And here's the DCM mouse, also at 2 months. Its relaxation is not swell either, PS, but completely different morphology. So this is a great phenocopy, I would argue. So that's where we start. We know we've been able to generate the phenocopy in vivo, and that's great. So now we did a number of biophysical studies, basically looking to see what was going on. And the most important thing here is this down below, this is this down here, is the difference here for RL, the hypertrophic and the DCM, with regards to cooperativity. So we all remember cooperativity, basic concept of sarcomeric activation, and it's governed by tropomyosin. Why? Because all those interdigitating tropomyosins basically transmit throughout the entire thin filament the activation state. It must work in concert. It's a little bit like synchrony in the heart. If you have one broken tropomyosin, the whole thin filament goes down, right? Because it pulls on the others. This is why these mutations are quite rare in tropomyosin. Because you have a very distinct possibility of nailing the whole thin filament. Just something to know. So this difference in cooperativity was really striking. You very rarely see an increase in cooperativity, and we really didn't know why this would possibly be, but we thought it might be important, a very important difference between the two. This is the basic biophysics. The main point here is this is the helical wheel. If I take that coiled coil, I slash it down the middle, and I look down the barrel, this is the orientation of those two helices, helix 1, helix 2, and the position of this D230N is actually on the outside as opposed to the inside where you'd have salt bridges and hydrophobic interactions. The key point being, and this was quite shocking to us, quite frankly, because very, very few mutations are on the outside because they're dealing either with the solvent or with another protein. Okay, so that was kind of an interesting thing. And here's RL. This is the older version of the computations just done on fragments. And what you can see, if you look right here, this is where the mutation is here in red. This is downstream. Remember I told you, it propagates. Here's the normal structure after a simulation. See that kink? That's what the mutation does in RL. Okay? So we've got all of these biophysical properties, but we're still head-scratching because it's actually hard to do these sorts of experiments on fully reconstituted thin filaments. Okay, that was actually, it's been a continual burden to us. Because when I talk about that coupling, when I talked about that before in that other figure, we need to use a fully reconstituted thin filament to match the model. I need to be able to compare these two things. So the model took forever. It took us a good year and a half to make this. So this is, really go back to chemistry, right? Differential scanning calorimetry, GOO, right? That was probably really this thermodynamics, the first part of chemistry when you were a freshman. All I want you to look at are these peaks. And this is just basically putting heat into the system and seeing the thermal transitions of this complex structure and figuring out what's unfolding first, because that gives you an idea about the stability of the system. Here we are trying to figure out this cooperativity. This middle peak is a measure of cooperativity. And here what we can see in blue is wild type. This widening of the peak here for the RL means that the cooperativity is going to go down. It's going to be more wiggly. Here, because it's steeper here and more narrow, this full width half max, it's going to be stiffer. Okay, so now we finally have a biophysical concomitant to go with those fiber studies that I showed you before. So it's starting to match up. But how do we correlate these sort of structural findings to structure? Because that's what we need to do now. Well, that was a big old problem, basically. First of all of this. Second of all, there was no structure available that had TNT in it. All of the previous studies, every time you put TNT in, everything would basically fall apart. So this took another year or two to figure this out. And I'm skipping ahead, but using the model, so-called, this is the hairy picture with all of the side chains. And basically, we modeled this full thin filament here. Again, this is Steve's model. And then we used FRET. In other words, we did structural measurements of the distance. This is an old technique, very difficult to do in a fully reconstituted thin filament, especially with a dimer. I won't get into the technical details. Just looking over here, this is what the raw data looks like for time-resolved FRET. And all you need to notice is that this light blue down here as opposed to the green, see how the time is faster, the decay time is faster? This means it's closer. That means these 2 points are closer together. So umpteen million, literally, experiments later, we actually were able to show what happened. This is a compilation of 1-4 students. Right here, if you see these red arrows in the middle, showing that across this domain here, when you have D230N down here, this whole system compacts. They all get closer. Okay, so keep that in the back of your mind. While R92L expanded. Remember that kink I showed you from the fragments? That kink straightened out, in this case, this molecule. You can see a little bit of a straightening and a turning out. This is the model now. He then went to the model, and I asked my collaborator to put these mutations into his model, and what he found in yellow is the wild type, the normal. In blue is D230N. You can see it's moved, it's turned, and it's closer. And R92L above has turned actually in a different way and is farther away. So what does this mean? Basically, that they have opposite effects on helical packing. The packing of spaces directly impacts flexibility and therefore cooperativity. And the overlap is exquisitely sensitive to these sorts of things. So our idea of the mechanism is that it involves a compensatory myocellular response to changes in flexibility and cooperativity that have a strongly dominant effect on thin filament function. So it's almost like it's a combination of effects. And the overlap itself, which I described as this swivel, can be modulated. Something to remember that I didn't mention before is that these mutations, in general, you can imagine, don't break the sarcomere, because that's death, right? There's no way to get around that. If the sarcomere becomes so acutely or chronically, broken or disrupted, you can't contract. So that's not happening. People who survive actually have lives. All these mutations are doing is they are in some way changing the function of the sarcomere. It's tolerated to a degree. And then the remodeling is via this compensatory changes over time. So does that sort of make sense? So that's what we're arguing, that in this overlap, there's a zone, if you will, and I have a figure that I find more confusing, so I don't use it. There's a zone of tolerance with regards to the flexibility. But that if you compact them past a certain threshold, the whole overlap becomes stiff, cooperativity goes up, and that generates a very specific response from the rest of the cell to try to mitigate this effect. Does that make sense? And RL is exactly the opposite. So what kind of differential cellular response am I talking about? I'm probably more or less going to finish on this. I'm going to go through the calcium part in a minute. Something like this. So for those of you, this is RNA-seq. So basically, it's a way to transcriptionally profile a tissue or a cell. And all I want to show you, so these different colors basically represent whether something is at the transcriptional level is upregulated or down. Blue being down, red being up. This is from these two mice. This is from the D230N, is the DCM model, and HCM from the R92L model. In this case, this is a huge study. This took forever. What we've done is we've paired, and we've looked at 1 month, 3 month, and 6 month, because I want to study that progression. I want to know what's going on, what's being, activated here. And all I want you to take home from this, don't look at all this, make you crazy, is the difference in the colors. PCM, it looks like there's an enormous amount of downregulation. HCM, a lot of upregulation, which doesn't really say all different pathways. So we're sorting this out. I want to switch down to this really quickly. This is remarkable, at least from my standpoint. This is at 1 month of age in the heart. Okay? Immediately, the cell basically turns on totally different sets in different directions of transcriptional activation. So is this part of that compensatory? Sure it is. Can we attack different pathways and see if we can actually modulate it? Probably. And that's what we're working on right now. So this was actually kind of exciting and sort of solidified everything. I'm just going to spend 2 seconds on this last part so we can have a good question and answer. I just want to point out that Carolyn Ho, so if you are looking for some really good literature on modern HCM that incorporates genetics, and Carolyn Ho, who has worked for many years with Christine Seidman at Harvard, and Charlene Day at Michigan, have really published some of the great work on this. And she basically showed that when you give diltiazem to preclinical, genotype positive, phenotype negative cohorts, you actually stall the development of the disease. And they were able to follow this up by when they stopped the trial, these patients started to remodel. So that's a little bit sea changing, and that's just diltiazem, right? That's sort of large common denominator sort of stuff, not very targeted. So we're excited by this because remember, in the past, we only treated symptomatic patients, right? So this is a little bit of a sea change, and we're all watching this very carefully because it just changes management. I'm just going to, as I say, I really do want to have questions, so I'm going to go quickly. I'm just going to point out that when you go back to this R92L and this R92W, so these are those two guys. This is a new one. They're both hypertrophic. This isn't. That's a single amino acid, same amount of protein. You can see, actually, this heart looks kind of smaller, and they have totally different physiologies. R92L has no effect on calcium handling. That's part of that compensatory change. RW has all sorts of change. So why is that? A single amino acid change. And you have that sort of differential calcium handling. Basically, what we found out was that this is using, in this case, looking at the kinetics of calcium coming away, looking for a measurement, looking for something to explain this kind of wild finding. We found the kinetics of release of calcium were actually very fast for RW, very slow for RL, kind of remarkable. This is actually steered MD, a different type of computational measure, which completely corroborated this finding. So now we have predictive value. So now I can take almost any mutation and assess what the effect of that mutation is. To give you an idea of how complicated this is, the mutation is in troponin T. The actual effect that I'm not showing you here is in troponin I, another complex part, which affects then release of calcium from troponin C. So now I think it's pretty clear why we can't just do experiments. This is why we need computation to tell us where to look. So I'm just going to say blow through this because I don't want to go through this. In any case, this is the question. Here's that dissociation. What kind of compensatory effect does it lead to? And answer, actually, of all things, is CaMKII activation. Modulin kinase is a very important kinase. It's in multiple tissues. Delta form is largely in the heart. And we found, first of all, when we gave diltiazem to these mice, we saw a differential effect where only improved function in RW, no effect on RL. Remembering, RL has no calcium derangement. So this kind of makes some sense, right? That's the one with calcium derangement. Well, when we looked at CaMKII, we could go even more specific than that. Activation of CaMKII here, only in RW. And, before anyone asks whether I'm blowing smoke, the important part was when we genetically went after CaMKII. What we found was, again, diastolic function only fixed. And this is a neat, I like this slide mainly because here you can see this is E to A ratio here. So you have normal CaMKII, and here we inhibit it genetically. Here's RL, where over time, this is 3 and 2 versus 5 months, you can really see that boy, RL just gets worse and worse and worse, right, when we don't treat it. And even when we do treat it, it really doesn't do very much. With RW, we can make it better by inhibiting CaMKII. It's actually I'm quite thrilled with this because it's exciting. And for my clinicians, so what's one of the most negative prognostic findings in HCM? It's atrial fibrillation. And these patients, because of elevated filling pressures, increased atrial mass, atrial dilatation, right, left atrial enlargement, develop AFib on top of these tiny little chambers. We all remember this from medical school. That's a catastrophe. They often, because they become dependent on their atrial kick because of those small chambers for the very hypertrophic patients, and they go down like rocks. The patient that got me interested in HCM arrested because they thought she had asthma and were giving her nebulizer treatments and threw her into AFib, and she collapsed. Probe on her chest, she had a heart that could fit in an elephant. It was a spectacular case, but that's what got her. And in my patients, the development of AFib, especially in my 30-year-olds, my 40-year-olds, is really a stroke. It's a catastrophe, and we really, really watch atrial size like a hawk. Well, here, what we found was that we were, with CaMKII inhibition, the atrial mass for the RWs over here, so this is early and then late, improved. Only 3 months, we were able to see an improvement in remodeling. And so, not seen for RL. So the importance of all of this is how specific this can be. And we're excited by it because think about it. Now we have a way, theoretically, if the calcium dissociation that I mentioned here drives this differential effect on CaMKII, well, that gives us something we can screen for theoretically, right? Remember, the RW patients also responded better to diltiazem. If I saw an RL patient, say an RW, without knowing their genotype, those hearts look enough alike that I'd give them both diltiazem. This work would argue it's probably not the thing to do. And this, as I say, is not just me, blowing smoke on this one, because more recently, papers have started to hit supporting the role of CaMKII activity in HCM. Very excitingly, more of Charlene Day's work that the nodal calcium regulatory protein is specifically post-translation dysregulated and auto-activated, which is what I just showed you. In sarcomere mutation HCM, a genotype-specific pathway for disease pathogenesis. And this is really important because patients with sarcomeric gene mutations, and not all HCM have worse outcomes. That's the Share Registry has shown that very clearly. If you have a sarcomeric gene mutation, your outcome is worse. Maybe it's because of things like this. Maybe your remodeling is more aggressive and earlier because of this auto-activation of CaMKII. It's certainly one part of the puzzle. And I'm not arguing that's the only part, but it is probably one of them. And so this is all very exciting because what we think we have is we have the back end, because all of this work was done in patient samples, end stage more or less, right? All they found were sort of signatures of CaMKII activation. We think we have a general idea of how it got there and where perhaps we can intervene over time. So I'm not going to go into that. So here is sort of the final rubric. And these are the questions we can ask. Can we biophysically change the trigger? Maybe. We're working on that. Can we think about CaMKII inhibition? Lots of there are trials going on in other diseases. I think HCM should be added to it with the caveat or the added excitement that we can subdivide HCM and in part on that calcium dissociation, which can be done in silico. So is it just calcium? No, we can look at phosphorylation. We can look at all parts of the thin filament at this point using our model and divide the disease up based on their effects on these different properties and start targeting, and I think doing a lot of exciting stuff, and certainly that's where the work is going. With the goal of getting rid of this part, the validation part, and going straight from computation to prediction. And why is this important? Because when we get de novo mutations, when your patient's reports come back and it's a brand new, say, thin filament mutation, there's no, we can use SIFT or polyphen or one of the other algorithms, but we really can't say very much about what that means. And I think by using these sorts of techniques and developing, better algorithms based on these computational measurements and validating them and then tracing them into animal models, we may actually get a much better handle. And what I envision is actually treating HCM patients a lot more like we treat heart failure patients, where we select which subclass of drugs new or old on their findings at the molecular level. I always close my clinical talks with this. So why does this matter, right? So this is a myosin heavy chain gene mutation. This is a valine 606 methionine. Now, if anyone here is sort of into HCM, you know that this has been reported endlessly as a benign mutation. Benign, just all over the place. Benign, benign, benign. Yeah, so don't believe what you read. So this is actually a family, I take care of this branch, where they basically my patient lost her grandfather, most of her great uncles, all in their 40s, as a matter of 40s and 50s, one after another. It was literally like about 10 years and everyone died. a long time ago. And down to about here, and the first gene mutations were linked right around here, and then they back-traced, and this really decimated this family. Over here is a 25-year-old who died while horseback riding. There was a drowning in here, over here, I think. Really, really devastating. So this is the family I take care of, and this is a lady who, her brother was diagnosed, and he recently died at 46 from a stroke. This is even knowing what was going on with him. Deadly genotype. This is his sister who was not genotyped, who was evaluated clinically in her late teens, found nothing. They said, go live your life. You're in good shape. You don't have what your brother has. You missed the family curse, which is what they call it. I got a phone call right after I'd gotten to Arizona about a lady who basically crashed during a pregnancy. So she had one little boy at 21, and then he was fine. Everything worked great. And then she was pregnant again at 38, and this was a nightmare pregnancy. I came on. Sure enough, she actually did have the genotype. She had terrible HCM, and in short succession needed an ICD and a myectomy. Bang, bang, bang. Child. And of course, because life is unfair, the little one was positive. So she had that baby, and she's like, right now, genotype her. So how does that change things? Well, it changes things, and here she is. This is part of our advertising materials. Here she is, right after she was born, about 6 months later. Here she is now. I just saw them the other day. Big grown-up girl. And so, at the end of the day, my job is to keep, because she has the same genotype as her mom and her uncle and her many. So my goal is to keep her from getting to where they did. Right? This is what moves you every day when you see these sorts of things. It's like, wow, I really want to go to her, her high school. We joke about going to her high school at graduation sometime and hoping that her heart really looks good, and we've figured out how to treat her. So that's the motivation. I think we're going to get there. And these are the guys who do the work. And anyone who's looking for a postdoc, I've got a slot. These are the guys who did all this work. Here they are in New Orleans, supposedly going to meetings, but I think they were mostly having a good time. So what can you do? Thank you very much.
Great talk. We'll get a few questions before we have to leave. Yes, Rob.
Leading to completely different phenotypes.
That's a great question. Actually, it's one of the reasons I usually show that family tree, where things were clearly very, very different there in terms of the time of onset and the severity to a large degree. So this is one of the great mysteries of genetic HCM. There are a lot of theories. Obviously, there is some question of environment, there's some question of sex. So there is still some feeling or some indication continuing from some of the early studies that male sex predisposes to worse outcome. So there's something about that. More specifically, the things that we really think are happening, and that we're finding this as we do more genotyping, is the effect of variants. The effect of variants in other sarcomeric proteins, variants in other components of signaling pathways that don't cause disease by themselves. But once you start to mix them in to a system that's already gone wrong and that are independently segregating, we think that's a big part of it. Beth McNally has shown this now repeatedly. So it's an interesting thing. My personal thought has always been that Titan's being kind of a bad guy here. So Titan has been strongly linked to DCM. And we're finding as we genotype, or as we sequence this enormous protein, we're finding endless numbers of variants. Interestingly enough, Titan mutations have never been really linked to HCM. Kind of crazy. No one can sort of figure that out. But Titan, for example, does interact, obviously, with most components of the sarcomere. Most of us think that actually Titan variants are probably a bit of a driver in here in terms of the response. That's what we think. It's incomplete, and it's vexing. It really is. That's a great question. We struggle with it. Yeah.
Dave, yes.
Without making them crazy. Intervention is ways that many patients are converted to set their practice. It does create a little crazy by this disease. It's difficult and all of the variable symptoms that it helps. So, I don't have a great answer to that. We do look for patterns within families, so we focus very strongly on the men in that family. It still is individualized care, and so for this little girl, for example, how often do we echo her? How often do we look at progress? I really don't have a great
David, I'm wrap up. I think you're ready.
Sorry.
Gotta teach.
Well, I got a quiz. Do you want to stay for the quiz?
What quiz is it?
Oh, some chemistry. Would you like chemistry?
When I was interviewing for medical school, I went and I sat down to meet the guy who was going to interview for his MBAs, and he pushed across